like to give two talks. Okay, first one is some basic some problems in four-manifold theory, and second talk is a little bit more advanced talks. Okay, so if you are expert, then just ignore first talk. Okay. Doesn't work? Okay.
Do you know about it?
이걸로 넘길 수 있어요? 이거 아닐 것 같은데? Okay. Okay, that's okay. Okay. Okay, let me start with definitions of the manifold. You know, the manifold is one of the most important objects in mathematics, in particular for the geometers and the topologists. You know, the people studied this manifold. It's almost more than since Riemann. You know, Riemann introduced the modern notion of the modern notion of the space, so-called the manifold. Okay, so what is a manifold? The manifold usually do you have the pointer? Okay. Okay. So basically, the manifold means it's a locally Euclidean space. Okay. But for some technical reasons, okay, we just input the Hausdorff and separables is such a kind of notions. But basically, you can think manifold is locally Euclidean space. Okay. We just want this connected and closed. Okay. Then the manifold means, you know, locally the Euclidean space. That means if we have some open coverings, okay, such that each open set is homeomorphic to Rn, and on the overlap, then we usually call that a transition map. Then because it's locally Euclidean, then the transition map is automatically homeomorphisms from the open subset of Rn to open subset Rn. So sometimes we call it's a topological manifold, and sometimes we just call it a manifold. But you know, if we don't impose any further restrictions, then this is just the manifold. It's nothing interesting in some sense. But the mathematicians, for example, the geometers, they want impose some the geometric structures. Okay. For examples, you know, the transition map is diffeomorphic. Then we usually call the manifold is smooth or differentiable, the differentiable n-dimensional manifold if each open set is homeomorphic to Rn or open subset of Rn. Then we call smooth or differentiable the manifold. Okay. And also, in the case,
you can use this hand to
yeah, that's better. Yeah. In the case, if this transition map is holomorphic, then we call this manifold is a complex manifold. And then automatically, if this is a complex manifold, then the dimension is the twice of this M. Okay? That means, the locally this is open subset of the Cm. Okay? But besides this smooth manifold and the complex manifold, there are many other categories of manifold. Okay? For examples, there is very important category of the manifold, so-called symplectic manifold. And symplectic manifold is an even-dimensional smooth manifold which admit non-degenerate closed two-form. The closed means d omega is equal to 0, and non-degenerate means the omega wedge and omega up to the half dimension of this one is the volume form. Okay? And furthermore, this one is better. Furthermore, there are many other structures. For example, almost complex structures, and the complex we already explained, complex manifold, and also the finer class, so-called the Keller manifold. And let me just review about this almost complex and this one. The almost complex structure on smooth manifold is the smooth field of complex structures on the tangent space. What I mean, some manifold admits the complex structures on its tangent space, tangent bundles, even though the manifold itself doesn't have the complex structures. Of course, if manifold admits a complex structure, then automatically it admits the complex structures on its tangent bundle. But sometimes, even though its tangent bundle admits complex structures, but it does not guarantee automatically the existence of complex structures on its manifold. So in that sense, we call this almost complex structures. In the case, its tangent bundle admits complex structures. And also, as I already told, the complex manifold means it's a set of the complex atlas together with the bioholomorphic transition maps. Okay? When we have open covering, which is each chart is homeomorphic to Cm, and furthermore, its transition map is bioholomorphic, then we call complex manifold. And also, there's a Keller manifold. Keller manifold means the symplectic manifold equipped with integrable and comparable almost complex structures. Okay, let me explain about this one, integrability and comparability in a moment. And equivalently, this Keller manifold is a complex manifold equipped with a Keller matrix. Okay? So this Keller manifold is the final class than this complex, the category of the complex manifold, and also this complex manifold is the finer than these almost complex categories. Okay. The integrability means it has the vanishing, the Nirenhouse tensor. That is defined in this way. The Nirenhouse tensor is like this one. I think you learned this one at first graduate course in differential geometry. And that means if this one is equal to 0, then we can integrate the almost complex structure to, the complex structure, almost complex structure to the complex structures. And also the almost complex structure J on a symplectic manifold is comparable. In the case, we can, when the omega is given, omega and almost complex structure given, then we can define the Riemannian metric in this way. G u v is defined by omega of u and jv. Then it turned out this one is Riemannian metric on X. Then the comparability means they cooperate with this Riemannian metric, this symplectic form, and these almost complex structures. Then in that case, we call comparable. Okay. And the calorimetric means is a Hermitian metric on a complex manifold. Whenever you have a complex manifold, you can think Hermitian metric on its tangent bundle. Then and the calorimetric means is the Hermitian metric whose associated unknown form is closed. In general, the associated unknown form is not closed. But in the case this one is closed, then we call the calorimetric. Okay? And if the complex manifold admits this calorimetric, then we call it a Kähler manifold. Okay, as I explained, there are many categories of the manifold. The largest categories are just topological manifold. Okay? Whenever you have open covering, which is locally homeomorphic to Rn or open subset Rn, then it's a topological manifold. And in the case, the transition maybe is the smooth differentiable, then it's a smooth manifold, and almost complex, symplectic, and complex, and the Kähler manifold. This Kähler manifold is the final categories. Okay? Then if it is Kähler, then automatically symplectic and complex, and of course it's complex and like this. There is some examples which is symplectic but not complex, and also there is examples which is complex but not symplectic. Okay? And there are many categories, and the mathematicians doing in each categories. For example, the algebraic geometers and the complex geometers usually they studied this Kähler manifold, and that includes the algebraic varieties. And smooth four manifold topologists usually studied these smooth categories, and sometimes they also studied these symplectic categories. Okay? And also this symplectic category it's really important the object in manifold. For example, in the classical mechanics and the mathematical physics, the object of the symplectic is really a key role. And so nowadays there are many geometers that studying these symplectic categories. For example, Ruan is also studying this one, right?
Well, yeah, I like
this one? Ta, Kähler?
Kähler and symplectic.
Kähler. Okay. Yeah. I have studied these the smooth categories, and then I moved to symplectic, and recently in the last several years I also studied this Kähler category too. Yeah. Okay. These are some typical examples of the manifold. For example, one-dimensional case. What is you already learned this what is the one-dimensional connected closed manifold? Then S1 is the only the one-dimensional connected and closed manifold. You learned this one in undergraduate, right? But when two-dimensional case, you learned the classification of the surface, and that is S2 or the torus or the projective plane, real projective plane, and the connected sums of these. Okay? The all-oriented surfaces is classified by the connected sum of the torus, or it is S2, and unorientable case is classified by the connected sum of this projective plane. Okay? And the three-dimensional case, here's S3 and S1 cross S2 and the three-dimensional torus, and there are many. Okay? And n equals 4. These are the simplest examples with a four-dimensional sphere and the complex projective plane and S2 cross S2, and there are many. Yeah. And okay.
Are they all Kähler manifold?
No. What I mean is just it's a smooth manifold. And some of them, for example, this one S4 does not admit the complex structures. Yeah.
Can you give us an example of the symplectic form of one of them?
Which one? This one?
I mean, for any
For example, okay. Example of Kähler manifold. CP2. Think of CP2. Or S2 cross S2. They are the Kähler manifold.
Then what is
The Kähler form, simplex form. This is a Fubini's geometry. The associated one-norm form of the Fubini's geometry. That is the Kähler, the closed the Kähler form on the CP2.
like S2 with the volume form is the simplest example.
Yeah, two-dimensional case, this one and this one admits, the Kähler admits, complex structures. In fact, the volume form is the closed. That, yeah.
We can make one for S2 cross S2.
Yeah. So the, yeah, okay. Okay. Then, why the topologists and the geometers are interested in smooth four manifold and also in some complex four manifold, complex surface, which is the same as the real four-dimensional manifold. And why are the topologists and geometers interested in smooth four manifold? That's the basic questions topologists and geometers asked a long time ago. And there are many answers, but I choose this one. Okay, the few things are known until the gauge theory was introduced in 1982 by Donaldson. Okay. And it turned out dimension 4 is different from the other dimensions. And surprisingly, when we compare to the topological category or the complex category, the smooth category, what I mean, the people try to investigate some smooth structures for a long time, but so almost nothing is known on the structures of the smooth four manifold, except a few. For example, what is the smooth differentiable or smooth invariant is known, but nothing is known until 1982. And as far as I know, only known some theorems about the smooth category. What I mean in the geography problems is the Rocklyn's signature theorems. That means any spin smooth four manifold has a signature which is divisible by 16. Yeah, that's only only known the theorems about the smooth category in some sense. Yeah, of course, there are other examples. For example, the Miller found the exotic seven sphere example, but in four-dimensional case, actually, it's nothing known until the early 1980s. And furthermore, it turned out the dimension 4 is really different from the other dimensions. For example,
what would be the first example of some smooth, topological manifold which is not smooth? Do not have smooth structure.
What is the first examples?
I wonder if they find that earlier or later.
It's earlier. Yeah, it's earlier. Yeah. I think in around the 1960s, they
what
found.
What environment they're using then? If you say there's no classical. It's a signature invariant, right? Hawking theorem.
Yeah.
For example, can go
Yeah.
Hawking theorem. From this theorem.
Okay, so what's the difference? What is the difference between four dimensions and other dimensions? For example, if the dimension of the manifold is less than or equal to 3, then topological manifold basically the same as smooth manifold. What I mean, given any topological manifold whose dimension is less than or equal to 3, then we can always impose the smooth structures. What I mean, so we can extract open coverings from this topological manifold, whose transition map is smooth, differentiable, okay, as long as the dimension is less than or equal to 3. So that is the reason why the topological manifold is same as is smooth manifold. Because of this, when studying the three-dimensional manifold, there are some people studying this topological three-manifold by using some topological tools, for example, LATs or some surgeries. But also, some people study this three-dimensional manifold by using some differentiable tools, such as Ricci floor or some Riemannian metric. Yeah. There are many ways to study this three-dimensional manifold. Okay. The one of the reasons is basically the topological manifold is the same as the smooth manifold. So we can impose the smooth structures as long as this dimension is less than 3. And when the dimension is greater than or equal to 5, by using Smail's H-covariance theorems, then we know there are at most finitely many smooth structures on a given topological manifold. What I mean, whenever we have topological manifold whose dimension is greater than or equal to 5, then you can impose at most finitely many smooth structures, including empty. What I mean, some topological manifold does not admit smooth structures. But the point is at most finitely many. And we didn't know at all until until the mid-80s, the dimension 4, whether there are many smooth structures or the unique smooth structure or the finitely many or infinitely many. Yeah, that is okay. So that is the reason why we didn't know anything about this four-dimensional case.
So in this case, you assume topological manifold concept and connected?
I assumed it's closed. Yeah. We don't. Okay. Of course, there are some other examples when manifold is closed or it's an open manifold, but in here we just assumed no boundaries the connected. So it's a closed. From the start, I recall assumed in the connected and closed.
So what do you mean if you have the two different smooth structure, then you mean that two smooth structure is not compatible? So
that means okay. Here's a smooth manifold, supposed manifold. Okay, this one has. Suppose we have this one has two smooth structures. Then we call this is different smooth structures if we can't find diffeomorphisms. Let's say these smooth structures, and that means if there is a diffeomorphism, say H from X1 to this, then we call these and if we can't find such diffeomorphisms, then we call this X admits two different smooth structures. No. No.
For example, if we share Riemannian structure, okay, geometry,
Mm-hmm.
so maybe you can use using the volume or what's the name for something like that, no?
I have no idea. No.
So how did you prove that?
This one? Oh, I forgot. But that follows from the H-cobordisms. You know what H-cobordism is? Okay.
Yeah.
Okay.
Yeah, I think most powerful approach in differential topology in higher dimension is Morse theory. I believe it has to do with Morse theory. But detail is have to check.
Yeah, but you know the H-cobordism theorem is proved by the most
Exactly.
yeah
That's
Morse theory.
That's
Yeah.
the major field in top.
Yeah, but the proof of this fact is something different. Yeah. Mm-hmm. Okay. So what is the goal of the four manifold? In particular, the geography problems of four manifold. Oh, I forgot. What does it mean, the geography problems? You know, the geography problems. Yeah, that comes out later. In fact, you know, in other words, geography problem means the classification problems. Okay? Yeah. So you may just think that geography problem is a little bit more than the classification problems. That is its meaning is a little bit different. Let me tell you later about that. Okay, what is the goal? Goal is to classify simply connected, in fact, topological or smooth or symplectic complex four manifold. But in topological category, let me tell you later in a moment, and Mike Friedman proved the classification of simply connected topological four manifold. And then as the next step is to classify simply connected smooth four manifold, and sometimes symplectic and sometimes complex manifold. And why is it simply connected? We import simply connected. You know, its fundamental group is, in some sense, fundamental group is the most, in some sense, is elementary and powerful invariant for the topological manifold. For examples, dimension 3. When you try to classify three-dimensional manifold, then fundamental group is the key ingredient. How to use the fundamental group, and sometimes you want some subgroups for the torsion-free is a subgroup inside the fundamental groups when you try to classify three-dimensional case. And what is the Poincare conjecture for three-dimensional case? That means only trivial fundamental group, the closed trivial fundamental group in three-dimensional case is S3. Okay, that means in a three-dimensional case is a fundamental group is really important. But in four-dimensional case, it's nothing true. For examples, for every finitely generated presented group, then you can find smooth four-dimensional manifold whose fundamental group is given this G. Furthermore, you can construct a symplectic four manifold with a given fundamental group. Okay? So this fundamental group, in some sense, the fundamental group in four-dimensional case, fundamental group doesn't play a role to classify. Okay? And the people think when you try to classify four-dimensional case, what is the simplest one? That is the simply connected case, right? And of course, some people still trying to classify whole topological four manifold for arbitrary group G, but at the first time, people trying to classify simply connected simplest ones. Okay? Yeah. And in smooth category and symplectic category, and sometimes it's the complex category. And historically, the algebraic geometers studied these classification problems in complex categories. Yeah. And after 1982, the people trying to, in particular topologists, four-dimensional topologists, trying to classify simply connected in smooth category and simplex category. But this complex category, historically, the algebraic geometers did first. This one.
You said there exists the most form okay?
Mm-hmm.
Infinite many or
Oh, sure, infinite many.
infinite?
Yeah, yeah, yeah. Okay. When you're trying to study four-dimensional, four manifold, given four manifold, for example, topological four manifold, whenever you have a topological four manifold, then there is no other geometric structures. But given topological four manifold, okay, we assume there is a closed and simply connected, and almost all classical invariants are encoded in this intersection form. Okay, what is the intersection form? You already know about this. That means, okay, because it's a simply connected closed manifold, there is no H1 and H3, and H0 and the Z, H4 is Z. So all homology, the non-trivial homology is in this second homology. And then intersection form is defined as the symmetric bilinear form on this H2. What I mean, you can take any element, the second homology class. This is four-dimensional. So whenever you have the second homology class, then you can realize this one as the embedded surface. Okay? So you may choose, okay, you may choose embedded surface representing this homology class alpha and beta, and then this intersection number means whenever you have two embedded surfaces in four manifold, generically they intersect at finite points, and at each point you can sign +1 or -1 depending on the orientations. When you compare the orientations coming from these two surfaces together with the orientation of x, if they coincide, then we impose +1. If they opposite, then we impose -1 and take a count. Because there are only finite intersection point, then this should be integer. Okay? That is intersection form. Okay? But by Poincare duality, this second homology is, by using Poincare duality, then this one is the second cohomology. And in fact, this intersection number is the same as the coproduct. Whenever you have Poincare duality of this alpha with, let's say, this is A, and the Poincare duality of this beta is B, then you can think A cop product B, that is a four-dimensional cohomology, and then evaluate the fundamental class of X. Then it's an integer. Then this one is the same.
This is a singular cohomology or singular homology?
It doesn't matter.
So it's always simplicial?
If you want singular, then you can use this, or also you can the drum also.
No, this is topologically you're talking about.
Yeah, topologically, yeah, singular homology, okay. Yeah. But homology, so basically, they are all the same.
Yeah, but are there any other homology for topological manifold besides singular ones?
No, we don't use drum homology. No. Yeah, but nobody use simplicial homology, right?
But there's no simplicial structure, right?
No. Yeah, sure, same. Yeah. But
Not differentiable manifold.
In case it does not admit smooth structures. Yeah. That's his, Yeah. So that this intersection form, contains all classical invariants. Okay. And the topologists in in 1940s, and the people trying to classify the topological manifold by using intersection form. Yeah. For examples, and then Whitehead proved this intersection form determines X up to homotopy. What I mean, if this, suppose we have X and Y, so topological manifold X and Y, then we wanna know whether this is homeomorphic or not. But Whitehead proved this intersection form and this intersection form is isomorphic. Then proved this is a homotopic. Yeah. Guys, if this intersection form is isomorphic. And what? Yeah, okay. I'm where's the eraser?
Eraser?
Yeah.
Maybe.
No?
On the back.
Oh, yeah. Thank you. As I told you, whenever you have four manifold, its intersection form is defined as symmetric two form of this. That means you can choose over integer. You can choose a basis. Let's say alpha to alpha k, alpha m, and alpha to alpha m. Then from this one, you can find m by n matrix. Okay? Q alpha I and alpha j. Then x and q sum y, this is isomorphic. In a sense, if you choose this as symmetric as m by n matrix, then you can find some q element, and if this one is where A is GLMG, something like that. Yeah.
Do we require the isomorphism of the homology group?
We can choose the basis. We can choose.
But they could have torsion, and the homology group could have torsion, right?
Torsion. I assume it's simply connected. Okay, no torsion.
I see. Right.
The more general version of the intersection form is the quotient by torsion. Yeah, but simply connect. Yeah. And the wall improved the Whitehead theorems. What I mean, X determines X up to H covariisms. What I mean, if QX is isomorphic to QY, then X is H covariant to Y. Okay? And in 1982, Michael Friedman proved, in fact, this intersection form determines X up to homeomorphisms. What I mean, if its intersection form is homeomorphic, is isomorphic, then X and Y is homeomorphic. In fact, it's not exactly homeomorphic. There are two cases. Okay? Yeah. So roughly speaking, this intersection form determines this X up to homeomorphic. Let me say about this. Okay, what is the Michael Friedman's result? Okay, because of this Michael Friedman's result, due to these results, Max Friedman got the field medal in 1986 with the Simon Donalds. Okay, what is that? That is, think about the category of all simply connected topological four manifold, and also think about the category of unimodular symmetric bilinear form over Z. The unimodular means whose determinant is plus minus 1. Then the coefficient is Z. Okay? So in general, the symmetric bilinear form does not have necessarily the determinant is plus minus 1. But we constrain the determinant is plus minus 1. That is called unimodular. And there is a natural assignment from the simply connected topological four manifold to the category of unimodular symmetric bilinear form over Z. That is given by intersection form. Okay, whenever you have topological manifold, then you can assign its intersection form. Then the theorem says, the Friedman theorem says, in spin case, there are one-to-one correspondence. What I mean, suppose you have x and y, then you can think it's intersection form qx and qy. If they are isomorphic, then they are homeomorphic in spin case. And in non-spin case, then there is 2 to 1. What I mean, whenever you have one unimodular symmetric bilinear form, then there are two simply connected topological non-spin four manifold whose intersection form is the same. Okay? And it turned out among these two, one admits smooth structures, the other one does not. So when we in non-spin case, if x1 and x2 has the same intersection form, in non-spin case, then one of these two admits smooth structures. And the other one, no smooth structures. Yeah. So when you restrict simply connected smooth four manifold, then there is exactly one-to-one correspondence between the category of the simply connected smooth four manifold and the category of unimodular symmetric bilinear form over Z. Yeah.
When you're looking at the form,
Mm-hmm.
can you tell it's coming from the spin?
Sure. Yeah, it's easy. Yeah. The even and odd. In simply connected case, the even form is equivalent to, say, spin. And odd means is non-spin. But in more general case, it's a little bit, the even does not get spin. If it is a spin, then its intersection form is automatically even. But the converse is not true in general. But it's true in the case spin, in the simply connected case. So you may, yeah.
For example, among the simply connected four manifold, we have maybe K3 surface and alternate surface, careless surface. And then the unimodular the intersection form is very nice. So yeah, bilinear form, maybe more condition, unimodular symmetry, or plus or something. Careless.
For Keller?
Yeah, careless. For example, alternate surface. Very nice. Yeah, intersection form.
Yeah, but in classical classification problems, this intersection form or any these forms are just a topological invariant.
Yeah.
So if you find some nice for Keller, well,
Maybe I think
no.
some intersection form is very particular, special. Yeah.
Yeah, no.
I think.
I don't think so. because you know, intersection form is just all okay, intersection form only contains all topological some properties, topological properties. What I mean in the classification sense. Okay. Let me view this one in other ways. Okay, all classical invariant. Let's think about all classical invariant. Okay, from this intersection form, so we can extract the following three numerical invariant. For examples, you know, Euler characteristic. Euler characteristic is that is because X is simply connected to first and third Betti numbers trivial. So the Euler characteristic is the second Betti number plus 2. But the second Betti number is the rank of this intersection form. Okay? And the signature defined by is the positive number of these positive eigenvalues minus negative eigenvalues. What I mean, this intersection form is a symmetric bilinear form. So we can diagonalize over Q over R, right? This whenever, even though all these entries are integers, so we cannot, in general, we cannot diagonalize in Z, but we can diagonalize in R or in Q because it's a symmetric matrix, right? So when you symmetrize, then some numbers on diagonal is positive, some numbers are negative. Because the determinant is plus minus 1, there's no zeros. Then the B2 plus is the number of these positive eigenvalues, and B2 minus is negative eigenvalues. Also, you can think this B2, this second homology is the isomorphic to self-dual harmonic two-form space. Harmonic two-form space, and the B2 is the same as the dimension of the self-dual harmonic two-form space, and the B2 minus is the dimension of the entire self-dual harmonic two-form space. Yeah, but topologically, to compute the signature is easy from this intersection form. Yeah. And these are, in some sense, the classical invariant. But instead of using this Euler characteristic and the signature, okay, the people prefer to use this C1 square and the chi. That is defined by 3 times signature and twice Euler characteristic. The reason is, in fact, this X admits almost complex structures. Then this C1 square is exactly the same as 3 times signature plus twice Euler characteristic. The C1 this is the first chunk class, and square is this is coproduct of the first chunk class. Then this is a 4-dimensional cohomology class, and they evaluate. Then they same as this one. The chi, we define this chi as this number. Okay, and it turned out if X is a complex manifold, this is holomorphic Euler characteristic, and that is the reason why algebraic geometers use this chi and the C1 square instead of using E and signature when you try to investigate these classification CF geography problems in the complex categories. So we prefer to use this chi and C1 square. And there's other invariant is the type, the even or odd. Even means that any self-intersection numbers, any self-intersection number is even. The odd means there is at least one element, second homology, whose self-intersection number is odd. Okay? Yeah. So these are the typical, the basic, the numerical invariant coming from this intersection form. And why is it important? And for examples, for the classification of X, in the indefinite case, this chi and C1 square equivalently this signature and order characteristic determines intersection form up to tie. And by Friedman's theorems, this chi and C1 square determines the topological type X up to type and homomorphisms. Okay, so in order to classify topological four manifold, simply topological four manifold, it's just classify this chi and C1 square and the type. Okay. Whenever you have two lattice points, then you can find simplified topological manifold, okay, whose chi and C1 square is this one. Okay. So the question is, then how about simply connected smooth four manifold or symplectic four manifold? Okay. Due to the Friedman's classification theorems, we know in topological categories, given chi and C1 square, then you can find smooth topological four manifold. But how about the smooth categories? And Friedman's Donaldson's proved, in fact, there is no simply connected definite spin smooth four manifold. And which means, in smooth category, this one is not one-to-one correspondence anymore. You can find some definite even some intersection form, but there is no corresponding simply connected smooth four manifold. So there is a big difference between topological category and smooth category. Yeah. So the people asked the existence questions. What I mean, which lattice point in chi and C1 square plane are realized as simply connected smooth four manifold? Sometimes simply connected symplectic four manifold or complex surface. That's the existence problems. The irreducible means, if X, whenever four manifold X and Y, then you can take fiber connected sum. Then by using this one, then you will see this one is something like that. QI, 0 and 0. So we want to find some basic building blocks. Okay. That is the reason why we want to find some simply connected irreducible, smooth, or symplectic four manifold. And as a second questions, the uniqueness questions. What I mean, if such a manifold exists, then how many distinct smooth or symplectic or complex structures on it when it exists? This uniqueness question is related to the how many smooth structures on a given smooth manifold.
I cannot understand what is the meaning of that point.
This
She wants to change a rational number.
No. Chi.
Why is okay?
Chi is divided by 4.
Yeah.
That is the same as B2 plus equals 1 over 2. If X admits almost complex structure, this is always integer. Yeah. If it admits almost complex structure. So if X is symplectic or complex, then it automatically this one is an integer. But in smooth category, this is not. Sometimes this is a half. What I mean, that is equivalent to say this B2 plus. B2 plus is odd whenever X admits almost complex structures. Yeah. Yeah. But in smooth category.
Point is in R2.
No. Chi and C1 square, in most case, this one is lattice point, integers. But in smooth category, you may think this one is even. But nobody studied for this case in these geometry problems because the Donaldson theory and Seiberg theory works only for B2 plus odd case. Yeah. And it turned out whenever X admits almost complex structure, then this number is integer. For example, X is simply connected, simplecting manifold or complex manifold, then automatically B2 plus is odd.
So you mean in case B2 plus is even case, you don't know about.
Nobody knows. Nobody knows.
What would be the example of such manifold? Like maybe, when it's even.
So
Think about that. CP2, connect some CP2.
Yeah, it's kind of decomposable, right?
Yeah.
But they're like irreducible ones?
No. As far as I know, no known. It's open problems. Yeah. So B2 plus even case is very. So the problem, one of the open problem is, can we find some irreducible smooth 4 manifold with B2 plus even? Not trivial case. For example, S4 not except this trivial case. Yeah. So even though gauge theory is what I mean, the Donaldson and Seiberg theory are very powerful tools. They only works for B2 plus R in simply in simply connected case. Yeah.
So what's the chi in the complex geometry? What's the meaning of chi again?
Chi is a holomorphic Euler characteristic. This one. If X means a complex manifold, complex structures, then this is holomorphic Euler characteristic. Yeah. And I told you the C1 square is 3 times signature and twice Euler characteristic. This one is always an integer. Yeah. Okay. So the geography problems of 4 manifold means it's existence problems and uniqueness problems. Okay. And
in the case of Donaldson theorem, she said that no simply connected definite speed starting. How about indefinite case?
Indefinite is they are yeah. They exist.
How is it? Definite
In indefinite, what I mean
definite non-spin.
is classified by optomorphic. Yeah. So what I mean, in indefinite case, all unimodular symmetric bilinear forms are equivalent to some of the interval of this one. Yeah. So definite case is a big problem. Yeah. So the geography problems means the classification. What I mean, the existence problems and the uniqueness problems. For example, let me think about this one in complex category first, because the algebraic geometers is this. Yeah. Algebraic geometers studied the geometric problems for a long time, and topologically they classify all complex surfaces. What I mean, complex surface means a real dimension 4. Yeah, so in the real dimension is a 4. So that is the complex surface is really the 4-dimensional manifold Okay, so anyway, in complex category, they classified topologically in the following three categories: rational or root surfaces, or minimal elliptic. We consider the minimal. This is not minimal, actually, most of them. Okay, let me tell later. And others. What I mean, rational means CP2, complex projective plane, and its blow-ups. And the ruled surface means CP1 vibration over CP1. That's rational ruled surfaces. Irrational ruled surface means some Riemann surface over Riemann surface. Riemann surface over vibration over Riemann surface. Okay? Yeah. So basically, you can think this rational ruled surface means CP2 and its blow-ups, or S2 cross S2, or P1 vibration over some Riemann surface, or like that. Okay? Yeah. And the minimal elliptic means it admits elliptic vibrations. What I mean that it admits some vibration structures, and the generic fiber is the torus. That we call the elliptic surface. And the TOPS, by using Seiberg theories, proved every minimal symplectic four manifold with B2 plus is greater than 1 satisfy the C1 square is non-negative. That means, but this one is still open problems, whether there exists or not, satisfying this, violating this one. What I mean, in this figure, in this coordinate, the TOPS theorem says any minimal symplectic four manifold with B2 plus is greater than 1 lies above this one. There's no symplectic manifold here, minimal symplectic, except this chi equals 1. But there is no known for this upper bound. And the people expect this is also upper bound for symplectic categories, but it's not proved yet. And in smooth category, it's much worse. What I mean, there's no known lower bound and upper bound. What I mean, still there are open problems. I think this 11A conjecture is one of the most famous conjecture in four-dimensional manifold. That means every simply connected spin smooth four manifold satisfy this inequality. What I mean, the ratio of the B2 and the signature is greater or equal to 11 over A. What I mean, in this plane, there are no known lower bound and upper bound, and 11A conjecture means probably every simply connected spin smooth four manifold lies above this 11.8 line. That's this line. But it's not proved yet. In fact, the fruta proved, in fact, they satisfy 10A. Yeah. And furthermore, there's no known irreducible smooth manifold lying between these, below this horizontal x-axis and this 11.8 lines.
11 over A has some kind of geometric meaning or arithmetic meaning?
No, this is not geometric. This have geometric meanings. Actually, you can find some optimal case, 11.8. How do you get this one? Just connect the sum of this En or En and some K3 surfaces. Then you can find this optimal one. What I mean, they are 11 over A. That ratio is. Yeah. But they are obtained by connected sum of them. But still satisfy this 11A. Yeah. So the people, actually I think Donaldson conjectured this one. Every simply connected spin smooth four manifold satisfy this 11 of. What I mean, they lies above this 11 over A. Yeah, yeah. These are the big the main open problems in four manifold. Okay, let me do quickly. Let me finish in 5 minutes. Within 5 minutes. Okay. for the first talk, what I mean. Okay. Okay, these are existence problems. And the uniqueness question, what I mean, given smooth four manifold, how many distinct smooth structures? And in last 30 years, the topologists and geometers are trying to prove this one. And now we know the most known simply connected irreducible smooth four manifold with B2 plus R admits infinitely many distinct smooth structures. Yeah. That's the main and big result by using gauge series.
Is that countable?
Sure, it's countable. What I mean, that's another problem. So what I mean, any closed four manifold, if it admits smooth structures, then should be countable because closed four manifold, in some sense, it also admits triangularizations. Yeah. So how many triangularizations you can take? That's countable and most countable many. Yeah. So any closed four manifold admits automatically countably many, and most.
Right.
But
Countable, right.
yeah. And it turned out most known simply connected irreducible four manifold admits infinitely many distinct smooth structures. Yes, this fact is really different from other dimensions. As I told you, if dimension is greater or equal to 5, the admits n most finitely many. But in four-dimensional case, there's no known single example which admits only finitely many, except what I mean, only all known smooth four manifold admits infinitely many, or most known, and we didn't know whether finitely many or not. Yeah. That point. And B2 plus one case.
So you don't know anyone that have only one. I mean, finite many.
No. There's no known single examples which admits only finitely many.
I see.
Yeah. Okay. Then why?
B2 plus equal 2 even case. That's 2.
As I told you,
Yeah, nobody knows. You said, yeah. But on two cases also you don't know.
Do people conjecture there's no such manifold? Irreducible?
what I mean, if it, in some sense, think about it's a smooth category and almost complex category, almost complex category, and the symplectic category, and some complex category. Okay? When you're trying to study this smooth manifold, in some sense, there's not much known some the powerful tools.
Right,
Yeah. So, in some sense, at least we want almost complex or the symplectic or complex. But this one is automatically P2 plus equals art, as I told you. Yeah. So, and the gauge theory, in particular Donaldson theory and Seibertin theory, you can't apply in P2 plus even case. So even though those invariants are smooth invariant, in practice, it's hard to get some information. Okay.
The theory, you need almost complex, or you need B2 plus?
In simply connected P2 plus R, we need this one.
So
Yeah.
you consider classical category this one.
Uh-huh.
How different? Can you guess? So how much?
You mean
Tomorrow, how much tomorrow?
you mean how many percentage?
Yeah.
You can do anything you want it, of course. You can always make it a little smaller. The question is.
Just moduli or something like
this smooth. Okay. Then different question. That's a different questions. What I mean, the moduli of some smooth structures or simplex structures, that's totally different problem. Yeah.
Well, if I understand correctly, people like smooth case, but there's nothing you can do, so we have to do this other thing because smooth is very hard.
Okay. I promise. Okay, let me finish it within 5 minutes. Okay, and then let's discuss the break time. Okay, why Donaldson theory and gauge theory, Donaldson theory, Seibertine theory are so effective to get such result? Okay? Then the answer is the following. The answers are the following. What? Yeah. If manifolds, four manifolds, smooth four manifold is connected to some of other two manifold with both B2 plus positive, then Donaldson invariant and Seibertine invariant are trivial. Which means if this is non-trivial, then this is not a connected sum of other two smooth manifold with this B2 plus both positive. And if one of these, when this is connected of the other two, and one of these B2 plus is 0, then X is homotopic to blob of another manifold. So from this fact, if we have some four manifold which is connected, which is non-trivial Seibertine invariant or Donaldson invariant, then we conclude that that's the minimal. That's not connected sum of other two. And in this case, we know the explicit formula. So just by investigating this invariant, then we know whether this is connected sum of other ones or the minimals. So the strategy is to find minimal smooth four manifold with Seibertine invariant or Donaldson invariant non-trivial. And the big point is this Donaldson invariant and Seibertine invariants are diffeomorphic invariant. What I mean, if X and Y are diffeomorphic, then these are the same. That means in some way, if we can compute Seibertine invariant or Donaldson invariant, and if they are different, then we conclude that that's not diffeomorphic. This is basic fact. So, in order to attack such problems, is to find smooth four manifold X and Y which are homeomorphic, but different Seibertine or Donaldson invariant. Then if we can find such an X and Y smooth four manifold, they are homeomorphic but not diffeomorphic, that different one, then they are not diffeomorphic, which means X admits at least two smooth structures. The one is from this one, the other one is from, think about this. If we can find X and Y, which is homeomorphic, so we can have that it's X, but we know this is not diffeomorphic. So we pull back. This one has one smooth structures, and we pull back the other smooth structures from this one via these homeomorphisms. So we have at least two different smooth structures. Okay? Because this is not diffeomorphic, this can't be diffeomorphic. Okay? Yeah. So this is the strategies. Okay? And in the last 30 years, the topologists oops. What's wrong? Yeah, in last 30 years, the four manifold topologists constructed many tools. All of these are some surgeries, and when they performed these surgeries and developed this one, and they also find formulas how to compute or how to trace the Seiberg-Witten invariant and Donaldson invariant changed. What I mean, in some sense, these are the topological surgeries, and they knew these are known before 1980s, but they don't know whether this one can change, whether they can change smooth structure or not. And by using Donaldson or Seiberg-Witten theories, they perform this one, and then they trace how those invariants changed. And then they found the formulas, and they turned out under these surgeries, they can change smooth structures. What I mean, suppose we have some smooth four manifold, and suppose we know Seiberg-Witten invariant or the Donaldson invariant are known for this case, then apply those surgeries. And from this one, we get the new smooth four manifold. And most of this one, not most of them, some of them, from this one to this, when they change from this one to this by using these techniques, then among this one, they are homeomorphic, each other. What I mean, XPQ, XP prime, Q prime is homeomorphic. Okay? And in some sense, this is just a topological result, not deep result. And they also traced compute its Seiberg-Witten invariant. That's the hard part. Whenever from this one, suppose we have known Seiberg-Witten invariant, and they perform those surgeries to get the new smooth four manifold, but finding or computing Seiberg-Witten invariant or Donaldson invariant is very hard problems. And due to the effort of the many topologists, top topologists, they knew how to compute Seiberg-Witten invariant of this one. And then from now, then they compare this one. If some of them is different, then we can conclude these are not diffeomorphic, but we know homeomorphic. So we can apply that strategies. This is the reason why it's effective.
The knot surgery here, is it the surface that is not hidden?
It's a different. No. It's that introduced by Fintuchel and Stern. Yeah.
Break first.
Okay. Yeah.
Are you finished?
Yeah. Okay. Let me stop here. Okay.
Yeah. Sounds